So once you've done an experiment thinking about the spring constant, you pop, this is today's lesson, the spring constant, it's whatever of June it is, you're happy to be doing this. Linear elastic distortion, where it stays within its elastic limit. The equation you need is F equals kx, so F is the force that we've applied to it, so how many newtons worth of force we've got pulling downwards. K is the spring constant, so how stiff the spring is. So this little spring here is quite easy to stretch, it's not got a particularly high spring constant. And this really thin spring here that I had to go with is really, really hard, so that'll have a really stiff spring constant, okay, and a very steep line on the graph. And then x is the measured extension that you used with your ruler, okay? So this is quite important. If you measure the force and the extension, the only variable in here that you don't know is k, which is a spring constant, which is different for different springs. So of course, what you now have to do is plot a graph, and you have to do it the wrong way round if you're going to get your spring constants so they make sense. Now normally the variable you change, your independent variable, will go on your x-axis and the one you measure goes on your y. However, this way round, because for a straight line graph with linear elastic distortion, y equals m times x, y is what goes on the y-axis, m is the gradient, of course you remember that, and x is what goes on the x-axis. So for this one, I'm relating it to the equation F equals kx. Please put force on the y-axis and the extension x on the x-axis, and then the gradient m will be what your spring constant is. And it's really easy. You can remember how to find the gradient. It's the change in y divided by the change in x, the gradient. So we could do a triangle for this one. It's nice and easy. It goes up by 10, and it only goes across an extension of 1, so the gradient for that is 10, and it'll be in newtons per centimetre for this, as I've used that. And this one here, it goes up to 10 in 10, so the gradient will be 10 divided by 10, so the gradient of this one, the spring constant, will be 1. So my nice, really stiff spring has a really high spring constant, and my much, much smaller spring has a very low spring constant because it's easier to extend. This one may go past its elastic limit really easily, but this one's going to have a very high elastic limit. So not only do you need to be able to do the experiment and use the equation, have a go at plotting a graph and finding the spring constant for each of those things. This will link really nice into next lesson where we look at the energy stored, but you have to know the difference between elastic and inelastic distortion. So, everything has an elastic limit. This spring has not gone past its elastic limit. If I was to get the teeny tiny spring and hang all my whole 10 newtons on it, will it go past its elastic limit, do you think?
Yes.
Very good. So if I pop that on there, stick it on the end, and I can hang it on, will it go back to the same length afterwards?
Not really, no.
No. Actually, that one's pretty good, so it's quite incredible. But I have a whole host of springs, as you saw, and they're all very different. They have different elastic limits. So, when we've got a linear relationship, which is a straight line, as I put more mass on, the force increases, the extension goes up by the same amount each time. That's within the elastic limit. That is what's called Hooke's law. When you put too much mass on the end, too much weight on the end of your spring, and it goes up to a point A, within that point up to A, it's within its elastic limit, because it's a straight line graph and it's a linear relationship. At A, it starts to extend but not proportionally. And what do you think is going to happen at B?
It breaks.
It will break, it's going to snap. Yes, very good. It's gone past its point of elasticity. It'll snap or it'll break, and you end up having nothing left there at all. No force applied because it's fallen on the floor. You can have a go at doing this. Please do have a go at doing this with anything you like. It doesn't matter if you don't have any scales even. You can get a spring out of a pen, a normal clicky pen. You can just take the spring, unscrew the top and take the spring out and hang things on it. That's absolutely fine. I used a hairband or a safety pin to hang up the bunny rabbits. You can do anything that you like, any way of doing this. And if I was to put the Haribo on there, they've got a mass of 190 grams. With the packet, that's about 200 grams. And if you think about that, that's 0.2 of a kilogram. So if you times it by 10 to get the weight, it's about 2 newtons, okay? However, if I put the Haribo and my 10 newtons on there, Do you think this spring has gone way past its elastic limit?
Yeah!
I think it definitely has. Look, it's not the same length now as it was when we started, is it?
No.
No. Okay, so I can't use that one anymore. It's broken. We've got something really lovely here. It's an enormous spider, but he's got really good elasticy legs. Now, there's a number of times I can use this before they get tired and the elasticity decreases. It's like hairbands, they eventually snap. So I could pull poor Spooky's legs lots and lots of times, and he'll eventually go back past his elastic limit. Is that a good idea?
No!
We'll keep poor Spooky as he is. Brilliant. Next lesson, we're going to look at the energy stored in elastic things. You need to be able to find the spring constant in order to do that. You've done a great job so far. Really good. Have a go at your spring constant. It's really nice and easy. Please watch the core practical video. Have a go at plotting your own graphs and remember how to find the gradient. It's really good revision. And hopefully I'll see you soon. But next lesson, we're going to do the elastic energy stored.
I'm going to stop it.